So we were looking at how voltages and currents are developed, okay, with the help of op-amp. And not only that, we looked at how this BJT actually helps us in driving the currents, right? So usually BJTs are used whenever there is a high load, and if we have to, drive these currents, okay, without any loss, then BJT really helps us in carrying out that task, okay, right? And then we saw the importance as to how the load current is actually not dependent on, the load resistor, but then it's very much dependent on R1, right? So I can say that IL is equal to V1 by R1. So if I change the value of this R1, it means that my output voltage is ultimately going to change. Okay, it's not because of the RL, but then it's because of the R1. And one more important factor, that we saw is if we don't have output currents, which is not greater than 25 milliamps, then what are we doing? We are actually neglecting the usage of BJT. Instead, we will look at circuits without the use of BJT. Right? Can you all recall these concepts? Yes, can you recall?
Yes, sir.
Oh,
Yes, sir.
fine. So, the only key here is, to remember and, understand as to how these circuits work. Okay, fine. So after that, we looked at how, we can actually make some changes. That is, we had two types. We had two types of load. One is the floating and the other one is grounded, right? So the previous one, that we saw was actually with the help of R1. So which means we can assume, or we can call it as the floating type. Okay. And here the RL is directly connected to ground. So we can say that, it's a grounded load. And here also you can observe that IL, the load current, is actually equal to the emitter, the difference between emitter and base. Okay, the currents between emitter and base. Fine. And we looked at PNP type of BJTs, right, which is which was actually helping us in driving the currents. Fine. So yeah. So the constant input voltage maintains a constant current through R1 and thus maintains BJT emitter and collector current constant. So here my idea is to have constant load current, right? So if I have to have this constant load current, then I should actually look at the equation, which is actually dependent on IE and it's dependent on IB. So how is that possible? How are we able to achieve that? Is being able to achieve when we give constant input voltage. Now remember, these were also called as converters, right? So what kind of converters are these called? Between one form to another form. Input was something and we get the output as something else. So we termed it as a converter. What converter is it? Yeah, what converter is it called as? It was called as voltage to, right, current converters. Right? So because inputs were given as voltages and we are expecting, or we are obtaining the outputs as current loads, current across the loads. Right. So for today, we will be looking another configuration of these current sources. Okay, and we will see how exactly these values actually holds good. Okay, so what I've done here is I've taken an example, and we will actually put those numbers here, and we will find out how relevant this actually works, and then later, we'll be utilizing a MOSFET, and we will see how it changes the driving capability. Right. So the voltage drop across RL, so we are looking at the drop here across RL, puts the transistor collector, okay, puts the transistor collector, this is base, collector, and emitter. So puts the transistor collector voltage above ground level. Okay. So whatever voltage drop that you have here, okay, which means there is some kind of potential here. So because of this potential, I can say that it is not at ground level, but then it is above ground level. Allowing a minimum collector emitter voltage of 3 volts. Okay? 3 volts. So approximately, if we calculate or if we use a multimeter and check, we'll be getting a voltage of approximately 3 volts. Okay. Right. The emitter voltage must be at least, okay, 1L into RL plus 3 volts above ground. Now, what is this exactly? We should actually look into the load resistance. Okay, so here you can see that this load resistance is given by what? RL. Right? Okay. So since it's actually given by RL, okay, we have a small conversion there, right? So I can say that it is IL into RL plus 3 volts. Now how is this 3 volts coming? I can say that this 3 volts is because of the potential drop across RL, and this potential occurs at this terminal here. So if it occurs, then it is approximately about 3 volts. So if I need to have a minimum collector emitter voltage, okay, that is if I have to have approximately 3 volts when I measure, to the emitter and collector, if I measure, if I need to have about 3 volts, then the emitter voltage, okay, must be at least, okay, IL, okay, into RL. Sorry, this is not 1L, this is IL. I into R, okay, which is VL, okay, the voltage across the load plus 3 volts above ground. So this addition, suppose I want to have emitter voltage of 5 volts, then what is going to happen? It is going to be IL RL plus 5 volts above the ground level. So the load current in figure, okay, so you can see that the load current in this figure, which is IL, is equal to IE minus IB, is actually the collector current. So this is slightly different from the current that you see here, I1, okay, because I1 here is dependent on V1 by R1. Right? Okay, but then IL here is equal to IE minus IB. Okay, just a moment. Now it should be fine. IL into RL plus 3 volts above ground. Yeah. Okay. So one thing that we should remember here is, if I have to have 3 volts, then whatever is the voltage here, okay, plus 3 volts I should keep. If I want to have say 6 volts, then whatever is the voltage here, okay, VL, okay, which is IL into RL, okay, so that one plus 5 volts. So ultimately I'll be able to obtain about 6 volts or 3 volts, whatever is my requirement. Okay. So the load current in BJT is actually the collector current, and this is slightly different from I1 because I1 here is dependent on V1 by R1, whatever input voltage that you're giving here, V1 divided by R1. So this is my I1. But IL is completely different. It is actually dependent on the BJT. You can see IE and IB, is dependent on the BJT, and the BJT in turn is actually dependent on the values of resistors R1 and how much of input voltage that you are giving. Okay, so the load current level is set by voltage drop across R1. So here the key factor or the important resistor here turns out to be R1 because it is indirectly, actually controlling the value of IL. How is it related again? Let me repeat. IL is dependent on currents with the transistor. Transistor is dependent on the value of this resistance, right? So again here we see that R1 plays a very important role. R1 plays a very important role in controlling the values of output currents. Okay. Even though this transistor, is actually helping in driving, but then it needs a supply, right? So the supply is created with the help of input voltage and R1. So R1 is a key factor here because I'm going to keep my input voltage constant. So I'm going to vary my R1 based on the levels of currents that or voltages that has to pass into the BJT. Okay. So the next, as I mentioned, we will look at including a Mosfet, okay? Including a Mosfet, and we will see how this actually works. Okay. So yeah. Now remember, this is not a BJT. This is a Mosfet. I guess probably in your digital electronic circuits, you would have seen MOSFETs, right? Like NMOS, PMOS, right? Which is P type of MOSFET, NMOS is N type of MOSFET, right? So all this you would have seen. And just to recall a few concepts, MOSFET is metal oxide semiconductor field effect transistor, right? And BJTs are bipolar junction transistors. So we are looking at MOSFETs here, okay, which is FETs, FET here, field effect transistor, and a MOSFET, okay. So we will apply both to the same circuitry. See, V1 remains the same, okay, plus VCC minus VE. R1 is here, RL is there. Similarly, RL is there, R1 is there, V1 plus VCC, and then ground. Okay. So ultimately, we are having the same, devices here. Okay, the resistors, the input values, and the op-amp, all this remains the same. Just that I'm changing the transistor. Previously, we had included a BJT, and right now we are here including an FET, and here we are including a metal oxide semiconductor field effect transistor. Okay. Now FET is used when I need the load current is equal to IS. Okay, IS. So whatever is the source, the same thing if I want across my load, then I will be using an FET. So we will look into it in detailed manner. So suppose I substitute a P channel FET, okay, in place of BJT. So what I'm doing, I am just kind of replacing this circuit here. So BJT is taken off, okay, and we are including this MOSFET here. Okay, so we are removing that, and we are putting this FET here. So if in case I am doing this, okay, and we are looking at including what type of channel, P type of channel. Now I think you all know what is P type and N type, right? Can someone tell me what is P type channel and N type channel?
Sir, in P-type, poles will be the majority carriers.
Hmm.
And in N-type, electrons will be the majority.
Correct. So which means, we have both majority carriers and minority carriers, right? But we are looking at the majority ones, right? The majority type. So here in this P channel, we have, the holes in majority and we have the electrons in minority. It's not that this absolutely no electrons. No, it's nothing as such. There are electrons. Okay, if there are no electrons and holes in combination, then the device wouldn't work. Fine. So we are replacing this BJT. We are taking that out and we are putting in FET. So why are we trying to do this? So that we want to understand how the performance of the circuit changes. Now, ultimately, whenever we change any device, right, we look at the pros and cons. If the pros are higher than the cons, then we try to go ahead with that. Just in many cases that holds good, right? Including the medicines that we take. If in case it is giving us more advantage than disadvantages, then doctor suggests to go for it, right? Similarly, here we look at circuits where we are trying to replace one type of device with another, and we can try and analyze its properties. If it's working fine, well and good. If the advantages are more compared to simple disadvantages, then yes, it will be taken for granted. But then, if the disadvantages are more than the advantages, then we wouldn't accept it. So here, we are trying to look at the properties. So let's look into it. Because FET drain and source currents are equal, okay, the drain and the source, okay. Now, one thing you should keep in mind is the source and the drain of a transistor are made up of the same way, okay, are made up of the same type. Now, let us say, this is my transistor, okay. So this is going to be my source, it's going to be my gate, and this is going to be my drain. Now keep in mind that this source and drain are made up of the same type of materials. So which means I can actually make this as drain, or I can change it to from this one to source. Okay, so which means I can write it as D/S or S/D. The gate will remain the same. The gate will always remain the same, right? And your channel formation and all, it happens here between the source and the drain, the channel formation, right? Okay, fine. So here now, let us look into it. The FET drain and source currents are equal. Now this is an important factor. Okay, please make note of this. Okay, the currents across the drain and source are equal. The load current is more precisely equal to the current through R1. Now previously we had seen that whatever current is coming through R1, okay, current coming through R1 is not the same as current across RL. If you can recall, it was actually dependent on IE and IC, right, when we had BJT. But here when we have an FET, okay, it is very clear that these currents are going to be equal. Okay, there's not going to be any change between them. Okay, so the load current is more precisely equal to the current through R1. So which means IL is equal to I1. Right? The presence of resistor R2 at Q1 source in figure. Okay, note the presence. So what I'm trying to do here is we have a resistance here, which is R2. Okay, resistance R2. This is required. Now you might think, so why is this needed? We didn't have previously, and here in this circuit also we do not have. We just have R1 and then we have RL. There's nowhere that we can see R2 included. Okay, so why is this actually included in combination with FET? So this is required when the voltage drop across R1 is not substantially greater than the maximum FET gate to source cutoff voltage. Now, as I mentioned here, okay, previously, remember I had drawn the diagram of the transistor, right? So you can understand that we are looking at VGS off. Okay, so what is this? Is nothing but the voltage between the gate and source. Remember, I had drawn the diagram of transistor, right? So we have a terminal called gate and we have another terminal called source. So the voltage between this gate and source is called VGS. Okay. So there's a small condition here. Okay, so in the cutoff voltage, okay, in the off voltage, so usually we have silicon at about we have threshold voltage of silicon of 0.7 and we have germanium the threshold voltage of 0.3. So what do we understand by these numbers? These numbers actually tell us that once the voltage reaches about 0.7, then the device would turn on. Once the device has an input of about 0.3, then in germanium devices, okay, it would turn on. So here we are looking at this cutoff voltage between the gate and source. So this is required when the voltage drop across R1, so across this resistor, is not greater than the maximum FET gate to source cutoff voltage. So whatever is the drop here across R1 should be very low. Okay, should be very low. It should not be greater than the cutoff voltage that we were giving here between the gate and source of what? Of Q1. Right. Now here you can understand that this transistor, okay, this transistor here, this transistor here has also three terminals. Right? So we have the gate, we have the source, and we have the drain. Okay, so gate is actually connected here across the op-amp. Okay, and usually the source of the transistor is connected to the VCC, right? And the drain is connected to the other potential. Okay. So why am I having this R2? So that it will maintain the drop across R1 as low as possible. Okay. Fine. So this is a junction field effect transistor, junction field JFET. So how using a junction field effect transistor instead of BJT gives a reliable current source since there is no device based current involved. So I do not have IB here. Yeah, unlike BJTs, I had IB, but here I do not have IB, but then I will have the gate potential. Okay, fine. So now, so we looked at what kind of voltages are here, and this currents, it's equal to R1. So in order to keep this voltage drop low across R1, I'm including one more resistor, and that is called R2. Why am I doing that? So that the voltage between the gate and the source, okay, the gate and the source is actually higher than the voltage drop across R1. Any doubts here, students? Any doubts, please feel free to ask. Can I proceed? Okay, fine. So now what we will do is, we will try and give this voltages and we will understand how it's actually functioning. Okay. So as an example, what we are going to do is we're taking VR1 is equal to 3 volts. What is this VR1? Okay. So voltage across the resistor R1 is about 3 volts. Okay. So the voltage at Q1 source terminal is VCC minus 3 volts. So VCC, let's say we are taking about say 12 volts, or 12 minus 3. Why is that? Why is that 3? Because I have 3 volts potential given here. Okay. If R2 is not present, so if R2 is not present, this is going to happen. What is going to happen? We are going to see that it's going to be VCC minus 3 volts. Or let us say, you know, R2 is present, then that minus factor is not going to happen. Okay. If Q1 requires VGS is equal to 4 volts. So if I want this to be maintained at 4 volts, okay, so just like how we saw BJT is equal to 3. So how we made it plus 3 volts, right? So we had taken that configuration, that equation where we are adding plus 3 volts, right? Okay. So if I want VGS, okay, the voltage between the gate and the source to be about 4 volts, okay, to the desired level, okay, the FET gate would have to be plus 4 volts with respect to the source. So whatever is the source, okay, so source plus 4 volts, okay. If you can recall, let us just go back, okay. Here for BJT, right, we had given IL RL plus 3 volts, right? So voltage across this load VL plus 3 volts. So the same concept we are applying here for our FET. So if I want it to be about 4 volts, VGS to be 4 volts, then what do? The FET gate would have to be plus 4 volts with respect to the source. So I must actually increase the voltage here to plus 4. This makes the gate terminal equal to VCC plus 1 volt, which is not possible. So here at the gate, since I'm giving another potential, so this becomes VCC plus 1 volt. So VCC is from here, right? VCC is from here, so plus 1 volt. So that's not possible, right? Because of all these resistances present. So in general, we have R2 resistor is necessary for reliable circuit operation. So what do you understand this reliable circuit operation? Again, we are looking at VGS off. Okay. So R2 is necessary for reliable operation, except where VR1, the voltage across resistor R1, is a minimum of 1 volt larger than VGS. Okay, so I can approximately see in the previous slide we spoke that the voltage drop across the voltage across R1, voltage drop across R1 should be much greater than VGS off. So how much? It's only about plus 1 volt. Okay, so that's the value. So it can be a minimum of 1 volt larger. Okay, so the minimum threshold that I am keeping here is about 1 volt, nothing less than 1 volt. Okay, and maximum it can reach to VGS off. Let's say VGS off is about 4 volts, right? So it can range from 1 to say 3.9 volts. So, or probably even 4, but it cannot go beyond VGS off. Okay, so the voltage across this R1 cannot go beyond VGS off. Now, the drain to source voltage of JFET. Now, as I told you, drain and source, right? So these two terminals, the drain and source. So the drain to source voltage of the JFET should also be at least 1 volt greater than the VGS of voltage. So which means we come up with this equation, okay, VDS minimum, okay. What is VDS? The voltage between drain and source, the minimum voltage between drain and source is equal to VGS of plus 1 volt. Why am I taking this plus 1 volt? Because that's the minimum level that I can attain. So it can go in the range of 1 volt to VGS off. Okay, so that's the maximum. So this range I am adding, so I am going to get a minimum drain to source voltage that can be applied for JFET, right? So a lot of analysis here, right? So the only way that you can remember is you can draw the circuit, right? Put down the equations and write as to what this VGS off is for, why are we taking 1 volt, and which is gate here, which is source here, which is drain here. And when I say VDS minimum, how it should be equated. So if you can answer these questions, right, you have understood the operation of the circuit here, right? So any doubts here, students? Now here,
No.
yes, please go on.
No, sir, I told no doubt.
Yeah, okay, thank you. So here, we are using a Mosfet. Okay, so this gives higher output currents. Okay, higher output currents. But then here we are going to have IL, which is load is equal to the source current. Okay, which is V1 by R1. So if in case your design needs, this type of configuration, right, where you need to equate both the load and the source, right? So you can go with FET type of configuration. If not, if you want a still higher, output currents, then you can actually include a MOSFET, okay, and that will provide you higher output currents. Now you might ask me, sir, how is it that BJTs and MOSFETs or JFETs, which is better? Now I would say that if in case your target is about 25 milliamps, then you reach out for BJTs, right? If you want to equate the equations, right? If you want to equate the input current and the load current, then you go with JFETs. If you want still higher currents, okay, still higher currents, then probably you can look at MOSFETs. But driving, when I say driving capability, let's say this is stage 1 of a circuit. Okay, now similarly, if I have one more stage here, okay, so let us say I am connecting these two circuits, so this becomes stage 1 and this becomes stage 2. So BJTs help in multi stages, in driving the output in multi stages. So from one stage to another stage, BJTs are very helpful. But then if I have a simple circuit and I'm expecting an output from a simple circuit, then MOSFETs are going to be the best option. And one more thing that you can keep in mind is these MOSFETs do have a lower power consumption, okay, than BJTs. So if you're thinking of power consumption, then MOSFETs could play a major role. Okay. The switching time, as I mentioned previously, the switching time between the highs and the lows, between ones and zeros, are higher or faster in MOSFETs compared to BJT. So BJTs are a little slower, but then the load carrying capability is higher. Okay, it is just like, probably you could think of a massive a transportation vehicle. So the capacity is going to be high, but then the speed is going to be low, right? So you can compare it with this sort, or probably MOSFETs you can compare with a smaller vehicle. The load carrying capability is not high, but then the speeds are going to be very fast. So I think now you have understood, how this JFET, okay, the junction field effect transistor, plays a very important role. Okay. Now next, let us focus on the MOSFET. So as I was mentioning, MOSFETs provide high output currents. So that is one advantage of having the MOSFET. Okay. So here in figure B, now we are concentrating on the figure B, right? So where we'll be looking into the inclusion of MOSFETs. Yeah. So use of power MOSFET for high load current situations. So there are MOSFETs which can actually work with low power, which cannot actually carry high currents, but then there are MOSFETs called power MOSFETs, okay, wherein it is operated at higher currents and voltages, right? So we are employing here power MOSFETs. okay, power MOSFETs, which means we are using higher voltages and currents. Why are we doing that? Because we need good driving capability. I cannot expect that from a low power device, right? So even though the power consumption is less, but then I will have to use its bigger brother, which is, which makes use of a higher uh, input. So in this case, there is no need for a resistor. So here, this resistor R2 is eliminated, right? I am not at all using this R2 resistor here in my circuit. So I just have R1, RL, MOSFET, op-amp, input voltage V1, resistor R1, and my source here is the same like the previous one, which is V1 by R1, and RL, okay, here is across the load, and the current is actually equivalent to the source, which is nothing but V1 by R1. So which means R1 is again playing here a very major role. So if I vary the value of R1, then it means that I'm going to vary how my load current is going to appear. So in this case, there is no need for resistor in series with FET source terminal, right? With VCC R1 and we had another resistor R2, right? So we are not having that, right? Because this MOSFET requires a gate to source threshold voltage. So we do not need cutoff voltage here, right? We are looking at threshold voltages. Now I have mentioned you what is a threshold voltage, students. What's the threshold voltage? The minimum voltage needed for so what is the threshold voltage?
To allow the flow of electrons, the minimum voltage required.
Yeah, which means we are actually trying to turn on the transistor, right? When the device actually turns on. Okay, so we are looking at gate to source threshold voltage, which is VG. TH is threshold, VG is the gate voltage. So gate voltage will be with respect to source. So we can even call it as VGS-TH or just VGTH. Okay, meaning that the gate voltage must be negative with respect to the source terminal when the drain current is flowing. So if I'm having this drain current flowing, then whatever potential I have here should be in negative. Okay, so why is this needed in negative? So that I do not have to depend on the resistor R2. Okay, so the drain to source voltage, which is VDS. Now, as I told you, it has source, gate, drain. So when I say drain to source, it means these two terminals. So drain to source voltage should be minimum 1 volt greater. Okay, so here also we are going to consider the 1 volt rule. 1 volt greater than the drain to source on resistance. Drain to source on resistance. Okay, not on resistance. This is on. Turning on the resistance. So the drain to source on resistance multiplied by drain current. So in short, we can even mention it as ID, the drain current, RD, the resistance across drain. Okay, that is RDS, drain to source resistance in on state. So how much ever is the value taken by this I into R combination, which is actually a voltage plus 1 volt. So I'm going to take 1 volt, and this should actually not be greater than this value. Okay, so which means we have a range here again, 1 volt to how much ever is across ID and RD. ID and RD, so which is nothing but the voltage across drain, the voltage across drain. So here also we are taking 1 volt. Okay, and the most interesting case here, the most interesting thing here is that we are eliminating another resistor. So one of the resistances is eliminated, and we are using MOSFET, and that too not a simple MOSFET, we're using a power MOSFET. So because of this power MOSFET, we are looking at operations to happen in with higher potentials, right? And we are looking at threshold voltages, okay, threshold voltages across gate and source. So the MOSFET requires a gate to source threshold voltage, which means the gate voltage must be negative with respect to the source. So if I check the gate voltage with respect to the source, it should be actually negative. So VGS should be negative. So if I can make this negative, then I can eliminate my resistor here. Okay. So if in case there is a resistor here, what is going to happen? This negative potential that needs to be maintained cannot happen. Okay, cannot happen. So that's what it says. In this case, there is no need for a resistor in series with FET source terminal. So this is the source terminal, right? Source terminal. Because this MOSFET requires a gate to source threshold voltage. Okay, so if this voltage is not there, okay, then it doesn't function. Okay, I need VGS. So if I put a resistor here, this MOSFET itself doesn't work. So that's the meaning of threshold, right? So if I give a minimum voltage, then only it's going to turn on. If that voltage is not there, which means it's not going to turn on. Requires a gate to source threshold voltage. So which means the gate voltage must be negative with respect to the source terminal. Why negative? Because we are giving a higher potential here at VCC. Higher potential is coming down, and if I check the gate voltage with respect to the source voltage, then actually it should be negative. With respect to the source terminal, when the drain current is flowing. Now there is actually an interesting concept in MOSFET. Okay, now this drain current actually flows whenever the device turns on and then it reaches its saturation. Okay, now let me just draw a graph, okay, and show you how this actually works. Right? So if I'm considering the voltages, right? If I'm considering the voltages, basically a transistor will have three regions, okay, and those three regions are cutoff, linear, and saturation. Have you come across these regions of operation for a transistor? Have you studied this?
Yes.
Yeah. Okay. So when I say cutoff, what is it actually referring to? I think maybe in your age you would have studied, right? Cutoff, linear, and saturation. So cutoff will be at this point, right? At this point, and linear is actually going to be, from here to here, because it is moving in a linear fashion, and saturation is actually a straight line. Okay, it's actually not a line like this because I've drawn, right? So let me probably cut it. Yeah. So it's going to be like this, right? Let's see if I can just erase. No, I can. Yeah. Okay, this seems to be better. Okay, so yeah, so from this point, okay, from this point to this point is actually referring to the saturation region. Okay, so this is referring to saturation, and this portion is referring to linear, and cutoff is actually when it is at the bottom. Okay, so this is cutoff. So cutoff linear, saturation. So we have three regions. Now, when it is in linear form, okay, when it is actually accelerating to become constant, okay, so this is voltage across currents, right? Voltage across IV characteristics. So this is my voltage here, and this is my currents here. Okay, so at a certain point, right, as I keep increasing my voltage, so my currents will start becoming constant. So that point from which the current starts becoming constant is called saturation. Now this current is actually referring to the drain current, so that is nothing but ID. Okay, so the current which appears across the drain terminal of the transistor. Okay, so which means it is actually referring to this ID. Okay, so at this point of time, you know, it will start becoming constant, and it is called a saturation mode. So ID will actually get generated, you know, when it has passed through the VGT, okay, which is threshold voltage, and then I still increase, you know, the voltage, okay. It is called VDS, okay, voltage between the drain and the source, okay, between this terminal drain and the source. So if I increase that VDS, so ID will start increasing. So this is actually my ID. So at this point it is increasing, and here it starts becoming constant, right? So ID becomes constant once the device is actually in saturation region. So here the ID is exponential, and here the ID is actually linear. So VGS and VDS. Okay, so these two are very important terminologies, right? VGS and VDS. Okay, so voltage across gate and source. Okay, so here voltage across VDS. So I should actually increase my VGS, and also I should increase my VDS. Okay, so at one point, as I keep increasing my VDS, my ID also will start increasing, okay, which is the drain current. ID will also start increasing till what point? Till it actually reaches this point, till the transistor gets into saturation region. So once it gets into the saturation region, the ID becomes constant, right? There is no increase in drain current, but then it starts becoming constant, right? So this is how, you know, actually your MOSFET functions. I hope you have understood whatever I have explained here, right? Students, any doubts, please feel free to ask. Can I proceed?
Yes, sir.
Okay. So, you know, you'll be learning about all these, you know, ID, VGS, VDS, cutoff, linear, saturation, about all these, threshold, all this we'll be studying in your upcoming semesters, right? I guess probably fifth semester where we'll be looking at CMOS VLSI design. So there exclusively we'll be discussing about MOSFETs and, you know, the PMOS, NMOS, okay, BiCMOS. So these are different types of technologies. Fine. So let's move on with the next concept. Yeah. So putting everything together, right? So we will probably solve a problem. Keep your calculators, a pen, and your notebooks handy so that we can make use of them. So we're going to use, you know, the figure which we had used previously. Okay, this D figure. Okay, to produce a 100 milliamp output to a 40 ohm load, and we're using the supply plus or minus 12 volts. Okay, and we're going to use LM108. So here we're not going to use, you know, 741, but then we're going to use a different op-amp which is code named as LM108. Okay, now this is a MOSFET here, right? We are looking at this figure here. Okay, So for the MOSFET, VDS max is equal to, so at the drain, the maximum that it can go is up to 12 volts, right? Because the supply is itself 12 volts, so I cannot go beyond 12 volts, right? Okay. And ID max, okay, the load current is actually given as 100 milliamps. So we have got this from a question. Okay, so it produces a 100 milliamp output. So as I was mentioning previously, ID, okay, the drain current actually becomes our final current that we need, or the output current that we need, right? So why am I telling you this is because the input, at the input side we are giving voltages, right? So here it can be in the form of VI, or it can be in the form of VGS, okay, which is gate to source voltage, and output expected is current. So here also we can see that we are kind of looking at a converter which is actually giving us currents when voltages are actually given at the input. Okay, so we are going to use a standard form here. Okay, P channel power MOSFET has VDS max is equal to 100 volts. So as I mentioned previously, whenever I'm giving you problems, right, I would mention these standard values so that it becomes easy for you to solve, right? So VDS max, we are using 100 volts, ID max is about 210, okay, when I'm using a power MOSFET, but then here we are sticking with LM108, okay. ID max is equal to 210, and RDS, which is the resistance between drain and source in the on condition, is 5 ohms. So what we will do here is we will just try to compare. Okay, yeah, we are going to use this power MOSFET as I mentioned. Okay, now this LM is actually the model for op-amp, it is not for MOSFET, right? So this model here, VP1008L, is actually a power MOSFET. So what we will do here is, we will try and use this model here, VP1008, okay, because it is suitable for Q1. So how is it suitable? Because it's a power amplifier, okay, and the ID max is about ID is about 210. Okay, so approximately, of course, it is a little higher, right? And RD is about 5 ohms. So we will use this configuration here. So the load voltage, okay, voltage across the load is ID into RL. So ID value we already have, right, which is 100 milliamps, and I'm going to use RL, okay, the load resistance. So we have it as 40 ohms, right? So you can see that 100 milliamps, 100 multiplied by 40. So how much are we getting? Are the values correct? Please check. 100 milli into 40. 100 milli. So are we getting this value? Okay, are we getting 4? Yeah. Okay, good. So this is fine for us. Okay. So we are going to use this equation, right? Previously, I had told you in the previous slide, ID RTS on plus 1 volt. Right? So this value, okay, this value I'm going to put it here. So ID, I know that it's about 100, and my RD, okay, RD I do not know. So what I will do is I will use the known value here. Okay, so that's the beauty of using standard values or standard devices, so that we actually know their values, so we can just use them, substitute and put it in the formula, right? So 5 ohms is here, so I will just put it up plus 1 volt. Please check and tell me if we're getting about 1.5 for VDS minimum. Again, what is VDS? The voltage between
drain and source.
Correct. Drain and source. So I am calculating the minimum voltage that can be between the drain and source of op-amp or transistor. So VDS is referring to the op-amp, or is it referring to the transistor or to the Mosfet?
Mosfet, sir.
Very good. It's referring to Mosfet. So are we getting 1.5? 100 milli you can multiply with 5, right? And to that value you add 1. So maybe you should be getting about 0.5 for the braces and plus 1. Are the values right? Yes, students, I need a response. Are the values right? 1.5 volts, are we getting it? Please calculate.
Yes, sir, getting.
Okay, thank you. So next, we will look at what is going to be the highest voltage across R1. So VCC R1 is the resistor which was at the top. So VCC minus how much of load voltage minus VDS minimum. So VDS minimum is between the MOSFET. So let us go back there. VCC, VL, and VDS. So VCC is here. Okay. VCC is here, and VL is here, and then the voltage across my transistor here, VDS. VDS, right? So VDS is going to be between this. Okay. And VCC is here, and then the load voltage. Okay. So VDS max or VDS minimum, we got 1.5 volts, and VR1. Okay, so what is the maximum voltage that can pass through? So VCC is 12 minus VL max, we have it as 4. Okay, and from here I've got 4, right? Previously calculated the load voltage maximum, right? IDE into RL minus the minimum value of VDS 1.5. So 6.5 is fine. 12 minus 4 minus 1.5. Yeah. Okay. Now next we have to calculate the value of R1. Right. So this was fine. 1.5, 6.5. Okay. Now R1. R1 is going to be whatever is the voltage divided by IL. Now why do you think I'm taking IL here? Because the currents are same, right? IL and IS, the currents are same. So 6.5 is here, and then 100 milliamps is, I have it here, the maximum. So please divide. I think you should be able to get about 65. 100 milli, right? We're getting it. 65. So as usual, we don't have a standard 65. So instead, what we will use a 56 ohms. Okay. So there's going to be change of about 4 or 5, yeah, about 9 ohms, which is actually not that significant. Okay. Next, VR1. Okay, VR1 is equal to which is voltage across resistance R1 is IL into R1. Okay. So IL, I have it here as 100 milli into R1. I'm going to use the design value. I'm not going to use 65 here. What I've calculated, these are theoretical values. Practically, I'm going to use a 56 ohm resistor. So I'm going to use 56 here instead. Okay. So yeah, should we be getting about 5.6 here? 100 milli into 56. 5.6 are we getting? So simple math, right?
Yes, sir.
Yeah. So V1 is equal to VR1 is equal to 5.6 volts. So V1 is nothing but the voltage which is across the input side, right? So let us go back here. Yeah. Say this IL is equal to IS, right? So that's why I took 100 milliamps IL, and to calculate, okay, to calculate the currents across R1, and this is my V1 here, right? And yeah, so using these formulas, right, we are able to calculate the values as to how much of currents. Only thing you should keep in mind, VCC value is important and the value of R1 is important. So you should be able to draw the circuit and actually put those values there. So how will you able to do? You will be able to do only when you know the formulas, right? So for example, these kind of formulas you will really have to make note and find out what is VDS minimum value. So using this VDS, I can find out the next thing. So ultimately, it's all a combination of formulas, right? So here also you can just make note of this VDS minimum. It's the same thing here, right? VL max is ID into RL, right? Some things are instantaneous, right? For example, VL, how do I find out VL? I have ID, okay, and I know the value of load, right? Resistance, so I will just multiply them, right? 40 is already there, so I multiply, so I get voltage across load. So some formulas are instantaneous, so which means when you see the circuit you should be able to come up with those values. So students, any doubts here with this problem? Yeah, any doubts here? Please feel free to ask. Is it fine?
No, sir.
Okay. Okay. Right. So now we'll be looking at differentiators and integrators. So I think we have very much worked out with mathematics using differentiation and using integration, right? So we will look at these circuits here. So I have lined up differentiators, the waveforms and the corresponding equations, right? And similarly for integrators, I have the circuitry, right? I have the waveform and of course few equations, right? So these are lined up for a lecture. Okay. So can someone tell me what is a differentiator? Why do we need a differentiator? If I want a part of the output, right? If I just want a small differential part of the input voltage, then I would be using a differentiator. Okay. So you can see that the circuit is pretty simple, right? We have an op-amp, right, and the capacitor here and the resistor. Of course, it's not mandated to have resistor here. Okay, it's not that mandated, but then we will see as to why we are using this resistor here. Okay. So one of the simplest of the op-amp applications that contain a capacitor is the differentiating amplifier. Okay, a differentiator which actually has a capacitor, or we can also call it as a differentiator. The circuit performs the mathematical operation of differentiation, that is, the output waveform is the derivative of input waveform. This is important, right? So which means the output is actually a part, or it is a derivative of the input waveform. Okay. So let us see what kind of inputs given and what kind of outputs that we are going to get. And also we will look into how is that we're going to get this V0 is equal to minus RF C1 dVi by dt. Right? So we will look into this concept as well. So the simple thing here, I'm going to have my outputs are going to have part of, or it's going to be a derivative or part of my input signal. So that is when I use a differentiator. Okay, so differentiators are also called as differentiating amplifiers. Differentiating amplifiers. And here you can see the difference, between the minus and the plus terminal should actually be about 0. Okay, so here are some of the waveforms. Okay, very interesting waveforms. This could be even asked for your interviews. In a differentiator, if a triangular wave is given, what is going to be your output, right? So your output is going to be in the form of square wave, right? Similarly, if you give this as an input to integrator, okay, if you give a square wave, you should be able to get a triangular wave. Right, so we can see a triangular wave input, and the resultant is actually a square wave output. So this happens when we pass the signal to the differentiator. So inputs are actually given in the form of triangular form, and the output is actually a square waveform. So you can rig up the circuit actually in your labs, and or probably using simulators. We have spoken about simulators, right, previously. So you can just rig up these, and you can check if you're giving a square waveform, then what happens. If you're giving a triangular wave, what happens, right? Okay, so I have taken here the example of triangular waveform, and we are obtaining a square waveform output. Now we will see the instances T1 and T2. So T1 is the time when the input is actually increasing, and T2 is the time when the input is actually decreasing. So here you can see that when it's increasing, okay, it's becoming a positive pulse, and when it is decreasing, it is actually becoming, the values are going down, reaching constant values, and once this level starts increasing, okay, it will the pulse reaches higher value. So we have two values here. Okay, so ultimately we have two values, that is plus V0 minus V0, two levels, right? So during the time T1, the triangular wave is changing at a constant rate of delta V by delta T. Okay, so the rate of change of voltage is actually constant. So what is this rate of change of voltage? Voltage changing with respect to time is in a positive manner, right? So its rate of change is a constant positive quantity represented by V0 plus V0 on the output waveform. Similarly, if we look for T2, it's going to be the opposite. So, this is the importance of looking into T1 and T2, right? So T1, your input value is actually moving from a lower point to a higher point, and during the time T2, it's just the reverse from a higher to a lower value. So similarly, during the time T2, the rate of change of input wave is delta V by delta T. So when we look at this delta V by delta T, it means that it's actually referring to the rate of change of voltage, right? And the two small incremental change. Okay, so delta is referring to a small change. Okay, just like dV by dt. Okay, so a small change in the input voltage, okay, divided by the time. And so the output is represented by minus V0. So here you can see that we have minus V0, isn't it? So this minus V0 is again going to, it's going to reach this level. Okay, fine. So it can be seen that the differentiation of a triangular waveform produces what kind of wave? Square wave. Okay, so triangular wave you give as an input. So like magic, you get an output in the form of square wave, right? So all this is because of the charging, the way that the value changes from one point to another. So let us look at this diagram here, right? So you have the input signal, right? So this is the TF, okay, which is the feedback. So differentiation of a square wave with a significant rise and fall time. So TF is your fall time. Okay, so yeah. So you can see that there's a small change here. Okay, so this is TR, which is nothing but rise time taken for values to change from a lower value to a higher value, and this is TF, so it is moving from a higher value to a lower value. So this is TF, fall time. Okay. So in this time only, okay, you can find that the pulses are actually going high and low. So that is your pulse here. So next, differentiation of a square wave with fast rise and fall times. So if I have a square wave, okay, and I am going to get this kind of spikes, okay, spike kind of waveform. So triangular gives me square, okay. And if I have a rise and fall time, then of course this is also going to be in the form of pulse, but then there is going to be small spikes. And if I'm going to give a square waveform, then I'm going to get a spike kind of waveform. So which means this is also a kind of pulse, okay, but then you can see here that there are spikes happening, right? So the most important diagram that you can draw in your examinations are is the first one, okay, as to how this triangular waveform is getting converted to a square waveform. I hope this point is clear. Can we move forward? Okay. Now we will look at some equations, right? So we will see how these are actually impacting. So we will look at node N, okay? So the node N is at virtual ground. Why is it at virtual ground? Because this is connected to ground via RF, right? So this also will be at virtual ground potential. So that is at node N, the voltage is going to be 0. So the voltage at this is going to be 0. The current IC through the capacitor, okay, you can see IC here passing through the capacitor C1, okay, is actually IC is equal to C1 into d by dt. Okay, so there is going to be a differential factor here, okay, differential factor of input minus how much ever voltage is across your node. Okay, so that is Vn. So if we calculate, okay, if we take the differentiation, okay, d by dt of Vi by Vn, okay, so Vn is anyway equal to 0, so Vi minus 0, so that is nothing but Vi. So I'm going to get C1 dVi by dt. Okay, so my input current is dependent on the capacitance charging and discharging of voltage with respect to time. That is the meaning. Any doubts here with the formula? How to understand the formula?
Yes.
Yeah. So IC is equal to C1 into dVi by dt. So my current across the capacitor is actually equal to the value of capacitance into what is the rate of voltage with respect to time. Okay. What voltage I'm talking about? I'm talking about this input voltage with respect to time. So R and C is a combination, and that is called time constant. R into C is a time constant. R into C is a time constant. Okay, so the current IF, okay, through the feedback network, the current IF is actually V naught divided by RF. So how much ever is my output voltage, okay, so that becomes V naught divided by RF. Now this V naught, how are we getting this V naught? We will just see here. V naught by RF, and there is no current into the op-amp. Therefore, the nodal equation at node N is, so there is no current here, right? Because it has high input impedance. So it becomes C1 dVi by dt plus V naught by RF. So since there is no current, right? So you know this Kirchhoff's current law, right? So you add them up and then it should give you 0. So V naught is equal to, what I'm going to do is, I'm going to take this one on the other side. So it's going to give me minus C1 dVi by dt. Okay. And V naught will remain as it is, and I will send RF on the other side. So on the whole, I will be receiving an equation which is V naught is equal to minus RF C1 dVi by dt. Okay, so that's the same equation that you find here. Okay, the same one that you find here. So what do we understand here? It is dependent on the time constant RC and the rate of change of voltage. Now this minus actually refers to that there is a phase shift of minus 180 degree. Why is there phase shift? Because we are using a negative terminal here. It's an inverted form, isn't it? So keep all these concepts in mind, from the first what all we have discussed. Thus the voltage, the output voltage V naught is a constant which is minus RF into C1. Always keep in mind this RF and C, wherever you find R and C. Okay, so just a moment. So wherever you find this R and C, okay, this is referring to time constant. R and C is time constant. So R here is referring to the feedback resistance, and C here is referring to the input capacitance. Fine. So times the derivative of input voltage and input voltage Vi, and the circuit is a differentiator. So you can see that it is dependent on the input voltage with respect to time. So there's a dividing that is happening, right? There's a differentiation that is happening. So the minus indicates one is 180 degree phase shift of the output waveform with respect to input. Fine. So we are looking at a capacitor here, and we know that this capacitor, okay, the current across the capacitor is C D by dt. Okay, now voltage here I have two voltages, V1 and Vi. So take those into consideration. So Vi gets multiplied. So ultimately, I am going to get C1 dVi by dt. Okay, and this V naught and RF we are getting just because of the gain. Now it's not only the CVI by dt, but then it's also we have to add up the gain, right? So V naught by, so this is nothing but our IF, right? So if we add up 2, then we should be getting 0 at that nodal point. Okay, so I hope this is clear now. So next we will move into something called integrators. What is this integrator? So just like how we saw differentiator will actually be a differential part of the input, here integrator does the reverse of what a differentiator does. So you can observe here, this resistor and capacitor are reversed. Okay, so the resistor was here and the capacitor was here, but then here it is reversed. Okay, and here it was a multiple, and here is a division, minus 1 by RC, that is a time constant VI by dt, but integration of the input voltage. Okay, so if we interchange the resistor and capacitor of the differentiator, the previous circuit, we have the circuit as shown here. So this becomes here as an integrator. So R and C if interchanged. An integrating circuit, now this is an important definition. Okay, it could come in your exams. What is an integrator? Okay, now explain the same with relevant circuits and equations. So the question will be in that form, and you will have to draw the circuit, explain what it is, and you can probably mention the equations and the type of waveforms and what is T1, what is T2, how is it going to be positive, how is it going to be negative during the rise and fall time, right? So all this can be mentioned. So this is an important definition here. An integrating circuit produces an output voltage that is proportional to the area under the input voltage waveform. So whatever voltage, the output voltage you are getting, the area of the output voltage will actually be proportional to what? The input voltage. Okay, so what is this? It is nothing but the amplitude is multiplied by time. So how much ever is the amplitude of the signal, that is multiplied by the time at the axis. Okay, so once we see the waveform, we'll be able to understand what is this actually area being proportional. Okay. So during the time delta t, now let us look at this figure here. Okay, so input here, I'm going to give a square wave and it's going to give me the reverse. Remember I was telling you, in differentiators, when we give a triangular wave, we actually get a square waveform, right? But then here it's going to be the reverse. I'm going to give the square wave and I'm going to get a triangular waveform. So here, it's noted as PW, right? So that is the delta T, and PW is nothing but the pulse width. Remember, we were talking about, how the pulses are, how the duty cycles are measured, right? So the on time divided by the total time period, right? So this is the pulse width. Okay, and here you can see delta T. Okay, and this is delta V, because this is time and this is voltage scale. So the amplitude is actually the voltage, and the width, this part here is the time scale. Similarly here also, this is the time scale and this is the amplitude. Okay, so during the time delta T, okay, during this time delta T, so which means this point minus this point, so that gives me delta T. The input voltage is a constant positive. Okay, you can see that it's a constant positive, just like how we had seen for Mosfets in the saturation region, right? So here also it is constant. Okay, so let me just notate, you will be able to understand, right? So it is constant at this point, at the positive side. Similarly, at the bottom, we can see that it is constant at the negative side. Okay. So constant positive quantity. So the output grows linearly from minus VOP, okay, that is minus output voltage, through 0 to plus VOP. So you can see that this is an inversion that is happening, right? So you can see that it's not an inversion, actually the charging of capacitance. So here you can see that the value has increased and then it has come here, And by that time, it takes time. So that is the time constant, RC, right? So RC, so it is getting charged and then it reaches the maximum. So that is my plus VOP. How it reaches maximum? Till the point that it is constant. From the point it comes down, okay? So you can see that this waveform also is coming down, but then, it's a slope. So we have two levels here, okay? So one is plus VOP, right? And the other one is minus VOP, okay? So two levels that we are looking at here. So this is passing the zero line here, right? So you can find this dotted line. So this is minus VOP, 0 plus VOP, 0 minus VOP. So three levels here, right? Minus, 0, plus, 0, minus. So three levels here. When the input switches to a constant negative quantity, okay, so to a constant negative, the one in pink, negative quantity, the output voltage grows linearly in a negative direction. So in a negative direction, it's a slope that grows linearly. So how does it go? From plus VOP, it goes to 0 and then minus VOP. So the input square wave, so this is a conversion here that is happening, right? So we have a square wave given, and in turn, we are going to get a triangular waveform, right? So integrators, many students have seen, they get confused between integrators and differentiators. The waveforms are interchanged. The positions of capacitors and resistors are changed, right? So do not get confused. Integrator will always have a triangular output for a square waveform. Differentiator will be the reverse, okay? And remember the positions of capacitor and resistor. Okay, fine. Let us move on to the next one, where we will look at some equations. So again, here we are looking at the nodal analysis, right? So we look at node N, right? We look at this node N and we write the equation. Vi by Ri, okay, or R1. So V1 by R1 plus Cf into dV naught by dt, right? Because this is connected to V naught is equal to 0 based on your KCLs. Or I can say that, I just take this dV naught by dt here is equal to, okay, this becomes, minus Vi by R1, okay, and this comes down to the denominator, right? So ultimately, it gives me this equation, right? So dV naught by dt minus 1 by R1 into Cf, right? Okay, so integrating now on both sides with respect to t. So my lower value is going to be 0 and my upper limit is going to be t, right? So I differentiate this with respect to t. So I take dV naught is equal to minus 1 by. So this is constant value, right? RC itself is a constant. So if I take an inverse of that, that's also a constant, right? 0 to t, and then I integrate the input voltage Vi with respect to t. So this gives me V naught, right? So it gives me V naught here, V naught with respect to t is equal to minus 1 by R1 Cf 0 to t. Now upper limit and lower limit, right? So here you can see that, V naught of 0 is actually the initial output voltage. So whatever was the value that you got previously, okay, so the same thing, but then this is at, at the denominator you can find R1 Cf, okay. So here we can see that it's a negative form, and this R1 Cf is a time constant, okay. So what do we understand by this? We understand that we are getting the integral form, okay. We are getting an integral form of the input waveform. So if the input waveform is square wave, we are getting a triangular wave. Okay, so this equation is important. Okay, so this equation is important. So please make note of this equation. We will be using this equation in our problems. Okay, so the next one, that we'll be looking into is the last slide for today's lecture. The circuit provides an output voltage which is proportional to the time integral R1 CF. Okay, so you can see R1 CF here. So this is nothing but the time constant of the integrator. So if I have to vary the values of this R and C, then ultimately that is going to, it's a multiplying factor here, right? So this can actually vary how my output voltage acts. Okay, so not only that, you can also note that there is a negative sign, right? There is a negative sign in the output voltage, and so you can understand that the integrator is also known as an inverting integrator. Okay, inverting integrator, because it is having a minus sign, so which means it is going to be a minus 180-degree phase shift. Okay, a 180-degree phase shift, so between the input signal and the output signal. Okay, so the other term used for this is inverting integrator, or I can just say integrator. Okay, so do not get confused, right? So we have this resistance here, right? I was telling you about this resistance R-com. So this resistance R-com can be equal to R1. So I'm going to make these two resistances equal. Okay, so this is usually connected to the positive terminal, right, to the non-inverting input terminal. Why is this done? So that we can minimize the effect of input bias current, right? So remember, we have input bias current IB max, right? So if you can recall, 741, we have about 500 nanoamps, right? So in order to decrease the effects of this bias current, I will have a small resistor here. So whatever small currents or values, whatever is here, will slightly be drained off to the ground with the help of R-com, right? So that is why this R-com plays a very major role. Okay, so I hope students, you have understood these concepts, right, with respect to integrators, with respect to differentiators, what kind of output waveforms that you're going to see, right? What are the circuits, and what is the time constant? When is it minus RF by C1? When is it minus 1 divided by RF by C1, right? What is the output voltage? When I give a square, when I give a triangular waveform, then I'm going to get a square output. So that is going to happen in differentiator, right? So many concepts, that we have looked into today. Just one thing is that, do not get confused where C and R are placed, right? Always keep in mind, differentiators will have resistance here in the feedback, and integrators will have capacitors here in the feedback network. So any doubts here, students? Can we end our lecture? Yes, can we end our lecture?
Yes, sir.
Okay, fine.
Thank you.